Before we had streaming services like Netflix and YouTube, which I hate to even use in the same sentence now, before we had simple video connectors like HDMI and DisplayPort, before we had HDTV or even DTV, which we transitioned to in 2009, we had analog video. Forget everything you think you know about modern digital video, because analog video was completely different. First of all, analog video did not use pixels. Images were drawn several times a second on a phosphorescent surface using an electron gun. Pew pew! This electron gun shot a varying degree of electricity at the screen to determine how bright or dark a given part of the screen should be. Every time it made its way from the left side of the screen to the right side of the screen, this was known as a scan line. The electron gun would then reposition itself at the left side of the screen, a little lower than before, preparing to draw the next scan line. Once it did this 240 times, it would then return to the top of the screen and draw the next image. This process would repeat itself 60 times per second. Another common property of analog video was that it was interlaced rather than progressive. Most modern video standards use something called progressive scan video, as this is what modern displays are designed to show. In progressive scan video, a complete image is drawn on the screen before drawing the next one. This image is called a frame, and the frame rate of a video determines how many times per second a new image is drawn. In fact, if you go to the settings of the YouTube video player, you'll notice the quality is expressed as a number and a letter. The number is a measure of the shorter edge of the video in pixels. So 1080p means this video is 1080 pixels high. The P actually stands for progressive, meaning that a full image is drawn before the next one is drawn. If this were an interlaced video, which YouTube does not support as of this taping, this letter would be I. In an interlaced video, only half of the image is drawn to the screen. In this case, the odd-numbered lines, first, third, fifth, and so on, were drawn to the screen. When the electron gun returns to the top of the screen, half of the next image is drawn. Since it drew the odd-numbered lines of the last image, it will draw the even-numbered lines of this image. The reason this was done was because engineers believed that drawing 30 full frames per second would look too jerky, and they wanted the video to be smooth. Due to technical constraints, the broadcasters could not transmit 60 full frames every second. If they did, the picture would only be 240 lines high, which was deemed unacceptable even in the 40s. The compromise was to transmit 60 fields per second, consisting of 240 lines each, to create a picture that is 480 scan lines high while still providing the illusion of smooth motion. The standard I've just described is known as the NTSC standard. NTSC stands for North American Television Standards Committee. Apparently NATSC just didn't quite have the same ring to it, or maybe they just didn't want to admit that they were Americans. As the name suggests, this standard was developed and used in North American territories. In Europe, a separate standard was created called CCIR. CCIR provided a picture that was 576 lines high at a rate of 50 fields per second. Color was added to the NTSC standard in 1953. This was done by adding a chrominance signal, which defined the color of each part of the screen, to the luminance signal, which determined the brightness of each part of the screen. Black and white televisions could still work with this system because they simply ignored the chrominance signal. However, the way the chrominance signal was modulated made it far more susceptible to interference, requiring frequent recalibration of color sets to ensure the colors were displayed as accurately as possible. Even then, the calibration was performed manually by a human, so there was no guarantee the colors would be perfect. Europe would receive a color format later in 1962. The engineers behind this standard knew about NTSC's shortcomings and worked hard to find a way to overcome them. The result was a new standard called PAL. PAL stands for Phase Alternating Line, named for the error-resilient modulation used to transmit the color carrier. This system was also compatible with the black and white standard that came before it, while remaining less sucky overall than the NTSC standard. While very few pieces of video equipment allow you to select whether you'd like to use NTSC or PAL, most modern televisions will happily display analog video in color no matter which format it's in. If you do get the choice, I'd recommend trying both to see which one looks best to you. While PAL color should look better in theory, it looked a little too dark and saturated when I tried it, but I'm an American, so it could just be a matter of what I grew up with. A final property of analog video is how many of its luminance and chrominance signals are transmitted independently from one another. In most cases, you'll see the luminance and chrominance signals transmitted together on a single wire or cable. This is known as composite video, since the overall signal is composed of both luminance and chrominance. However, it is possible to transmit the color information separately from the luminance information, to reduce interference between the two. Furthermore, it is possible to have two distinct chrominance carriers, one for the color red and one for the color blue. The green color signal is derived mathematically from the red, blue, and luminance signals. This is known as component video, since the luminance and chrominance components are transmitted independently over two separate wires. Since any one of these wires could be used to transmit a 480i image on its own, using 3 wires also allows for a larger image to be sent to the television, or for the same size image to be sent in progressive scan. Resolutions supported by component cables include 480i, 480p, 576i, 576p, 720p, and 1080i. One more thing to note about analog video is that it takes a moment for the electron gun to reposition itself after finishing a line, and even longer after finishing an image. This means there's a brief period of time after each line and image during which no picture information can be transmitted, and anything that is received during this period of time is not drawn on screen. This period of time is known as the horizontal blanking interval if it's between scan lines, and the vertical blanking interval if it's between images. Broadcast television stations and home media alike found several creative ways to take advantage of this otherwise empty space in the signal, but that is for another video. Thanks for watching, and I'll see you next time. Bye for now.